the more you look at these systems, the more you look at thermal systems, fluid systems, electrical things, mechanical things, when you simplify them down to a transfer function form, they all tend to take the same shape. They're mathematically very, very similar. Okay. And we're going to push that idea by further manipulating these into what are called standard forms. And there's a first order standard form. Output C over input R equals a gain number times 1 over 1 plus something S. Okay. Some people would argue that that gain number is separate and it's what you call a zero order system, but it's easier to think of it lumped in. So if you can get anything that you can manipulate its transfer function into that shape, that means it's a first order system. That means we will know exactly how it behaves. And I don't care if it's electronic or mechanical or anything else. That fluid tank that you did in the tutorial simplifies quite easily into that first order standard form. There are only two numbers that concern us in that standard form. There's a gain number and there's what we call a time constant. 1 over 1 plus something S. That something is the time constant. There's the gain. All the gain does basically is tell us how big the output is compared to the input. It's a size thing, nothing else. It just tells us about the size relationship between the output and the input. The time constant for that system is A upon K. And that tells us about the speed of the system. So there are two numbers. One tells us how big something is and one tells us how fast it is. Okay, so any amount of algebraic manipulation, if you can get it into a standard form, it's really easy to get that information. What do we measure time in? Seconds, thank you. If you go back to that model of the tank, that's the cross-sectional area up there, meter squared. And this K was the constant of proportionality relating pressure to the outflow, wasn't it? Yeah. Those of you that have done tutorial sheet 1, you might remember that. If you go back and look at the units in there, A upon K will work out as seconds. If it doesn't, we've done something wrong. But the units come out as well. So the size thing. This is relating depth of water to the inflow. K relates to how quickly the water falls out to the bottom. Yeah, it's that proportionality thing for the outflow. If I make K bigger, then I'll get more water falling out, which means my depth doesn't increase as much. So in other words, if I make K bigger, the size of the output is smaller. Which kind of makes sense. If I make K bigger, then this A upon K number becomes smaller. And what that means is that the speed of response of that system is faster. Okay. In the same way, if I make A bigger, then that A upon K becomes bigger. And well, you can answer the question. If I make my tank much, much bigger, cross-sectional area, does it fill up more quickly or more slowly for a given Q in? Slowly. Because it's got a bigger tank to fill. And you can see that that makes the time constant in seconds bigger. So it actually does make sense. The stuff is all true. So the gain is 1 upon k. The time constant for this system is a upon k, and that comes out in seconds. There's a second order standard form. This is the quadratic one with an s squared in it. I've now got 3 variables, 3 numbers to worry about. I've got the same gain number that tells me about the size, and I've got 2 numbers in here that tell me about the dynamic or the speed of the system, both of which you've come across before. So gain is the size one. It just relates how big the output is for a given input. The dynamic numbers are in here. Does anybody remember what omega n stands for? Natural frequency. It's the natural frequency of oscillation of that system. So I could, with a bit of algebraic manipulation, I can pretty much immediately pull out the natural frequency for that system. There's the other one, zeta. Anybody remember what that one is? Damping ratio. See, all that time doing dynamics was worth it, wasn't it? So I can also get out from the simple quadratic description not just the frequency of the system, but also how much damping it's got. And because I've forced my system model into this particular shape, getting that data is really, really easy. Okay, so long as I've pushed it into that sort of quadratic in the bottom. Omega n, undamped natural frequency in radians per second. Zeta is the damping ratio, and the last one we know about already is the gain. Damping ratio, of course, is dimensionless.